Hi there. This is day 17 on Euler Trails and Hamilton Paths. Let's get started. When we say an Euler Trail, we mean a walk which uses every edge of the graph exactly once. We're allowed to repeat vertices. In fact, we may have to. An Euler tour is an Euler trail that starts and ends at the same vertex. The graph is Eulerian if it contains an Euler tour. I'll show you an example. This graph is Eulerian. I can pick a vertex and I can trace through every edge of the graph exactly one time and come back to this vertex. For example, I can trace this edge, then this edge, go around the border here, and then I'll go around the circle, and then around this square, and then back up. You may have played games like this at some point as a kid, where you had to trace over the diagram without going over any segment more than once. This is what it means to be Eulerian. We can trace the graph without repeating edges. And return to the starting point. Leonhard Euler was a German mathematician who looked at this from the point of a problem of being able to navigate the streets and bridges of a city to perform a service and be able to navigate all the streets and bridges efficiently, so you didn't have to go over the same streets more than once. He solved a famous problem involving crossing bridges in a town called Königsberg, which, if you want to look up the problem, this is considered by some people to be sort of the origins of graph theory, is the problem that he solved back in the 18th century. Let's look at this graph here. And look at the degrees of the vertices. This vertex has a degree of 2. This vertex has a degree of 2. This vertex has a degree of 4, 2, 2, 4, 2, and 4. All of the degrees are even because for any vertex that wasn't my starting vertex, I had to come in and leave on 2 different edges. And I may have done that twice in this case. I came in and left, and then I came in and left again. But it takes a pair of edges to come in and leave. The starting vertex takes a pair of edges once to leave, and then once to finish up. And so every vertex ends up having an even degree if a graph is Eulerian. We have this as a theorem. A connected graph contains an Euler tour if and only if every vertex has even degree. A trail is different from a tour. It does not have to finish where it starts. For example, this graph here has an Euler trail. I can start here, go to the right, around this square, down around this square, and then come back towards the end and end here. And I started and ended at 2 different places. But that requires that I have an odd vertex here to leave from and an odd vertex here to arrive into. And so a connected graph can contain an Euler trail if there are exactly 2 odd vertices. And if there's 0 odd vertices, then every vertex is even, which means it has an Euler torus. It has one that actually does come back to where it starts. So these are the only graphs that can have Euler trails or torus, is whether they have 0 vertices with even degree or exactly 1 to start and 1 to end. And we have an algorithm to compute an Euler torus in a graph that has one. Let's talk about this algorithm for a second. The basic form of the algorithm is for a connected graph that contains only vertices of even degree. We'll pick any vertex in the graph and start drawing a sequence of edges that we haven't previously used until we get back to V0. And we'll have a circuit. We'll go ahead and call that circuit R0. If we happen to have used up every edge, then stop, because we found an Euler torus on our first try. But if we don't have an Euler torus, let's continue on, and we're going to increment this subscript by 1. We'll choose a new vertex that touches some edges that we've used and some edges that we haven't used. We'll follow any sequence of edges that haven't been previously used until we get back to VI, and we'll merge that circuit with Ri sub 1 and call that result Ri. And then keep going until we contain every edge. If we have every edge at this stage, we stop. Otherwise, we go back to step 3 and continue again. I'll do an example in a moment to walk through this process, but this is a recursive algorithm. Why does this algorithm have to eventually terminate? The reason it has to eventually terminate is that every time I increases, the number of available edges goes down. And since we only have a finite number of edges, if the finite number decreases every time we do this algorithm, at some point we will have used up every edge. Available edges drops to 0, which means we've used up every edge. We have to modify this graph if there are 2 vertices of odd degree. And we'll replace step 1 with, instead of choosing a circuit in the graph, choose a walk from the starting vertex to the ending vertex. That's the only change that we have to make if we have 2 vertices of odd degree. We have to then start at one of those vertices and end at the other vertex and make sure we do that. So let's use Hierholder's algorithm on this graph here. The first thing we do is we choose any vertex V0. So I'm going to choose this vertex here, and that's going to be my V0. Just start moving through edges until we get back to V0. So start walking. Until you get back to V0. So I'm going to start walking, keep going, keep going. All right. And now I'm back at V0. Okay. I have to be able to get back to V0 because every vertex has an even degree, which means every time I arrive, I take away one of those edges. I still have an odd number of vertices left, and an odd number can't be 0. And so I will always have at least one edge left to leave from. So I have to be able to get back to V0. Did we use every edge? The answer is no. So what we'll do now is choose any vertex which includes some of edges that we used and some edges that we didn't use. So I'm going to change colors here, and I'm going to let this vertex be V1. So choose any vertex which includes some edges from R0 and some unused edges. And what we'll do now is we're going to start traveling around this vertex until we reach, come back to it. So I can start going left or right. It doesn't really matter. If I go to the left, go around a circle. I'm not allowed to repeat edges, so I can't go up or to the left. I have to go to the right, I have to go up, I have to go across and through here and then back to V1. And so I have two circuits now, this red circuit and this green circuit. So at step 2, we start walking until we get back to V1. And did we use every edge? This time, every edge has been used. If we had not used every edge, we would choose another vertex, V2, and draw a new circuit onto the process. But once we have chosen every edge, what we're going to do now is merge these two circuits together. I'm going to start walking along my first circuit, V0, until I hit V1. At the moment I hit V1, I push the first circuit onto a stack, and I start traversing the second circuit until I get back to V1. Then I pop the first circuit off of the stack and finish traversing it. I just saved the circuit where I was and resume then after I've completed the second circuit. So start drawing on the first circuit, push the first circuit onto the stack and start drawing the second circuit. When I finish, pop the first circle back off the stack and finish it up. Okay? Let's try another example, a little bit harder one. Let's use Hirschhauser's algorithm to show that this graph has an Eulerian tour. Okay? I'm going to start by picking any vertex and follow edges until I hit my first vertex again. So I'm going to start right here in the center. This is going to be V0. And I'm going to intentionally wrap up quickly. Here's a circuit that starts at V0 and ends at V0. That's my first circuit. Well, I didn't use every edge, so then I pick a vertex that touches this circuit and some of the extra edges and call that vertex V1 and start drawing again until I get back to V1. Okay, so I'm going to go around this loop here, down, across, and back up. and that's my next circuit. I still haven't used every edge, so now I pick a vertex that includes some of the edges I have used and some of the edges I haven't used, and call that vertex V2. So let's look at this vertex here, call it V2. All right. I'm going to go up, over, and back. Oh, and I'm back at V2 already. And I still have some edges that I haven't used up. So I'm going to pick another color here. Find a vertex that I haven't used yet. Let's call this one V3. And start following along edges until we get back to V3. So we'll go around. The only edge I can follow now is this one here. The only edge I can follow around is this one down here. Then I have to go up, and then I have to go back down. And that gives me a third circuit. Or fourth circuit, because we started with R0. And now what we'll do is we'll put all these together. I'll go back and use my original color. Yellow doesn't show up real well here. I'm going to start at V0. And anytime I hit one of the other vertices, V1, V2, or V3, I'm going to stop. So I go along here, and immediately I hit V1. And so now I push R0 onto the stack, and I start following this circuit until I hit another vertex, V2 or V3. So I start following V1, and immediately I hit V2. So I push this circuit onto the stack, and I start following V2 until I hit another one of these vertices. So I go around V2, I finish that circuit completely. I don't hit any of the other vertices. I hit V0, but V0 is up earlier in the stack. So I pop off the R2 off the stack, and I keep going along R1. So now I've hit V3. So I pop down or push down. I still have one edge left on R1 to complete, and I haven't done it yet, but I'm going to start traveling along R3. So I travel along R3, and I come back to where I started. So now I push back and finish R1, and then I push back up or pop back up and finish R0. And that gets me a path that goes all the way through the graph and comes back to my starting point. It's a little tricky, but once you get through a few examples, you see how it works. It is definitely a recursive type of algorithm, though. So let's move on. A Hamilton path in a graph is a graph that includes every vertex in G exactly one time without returning to any of the vertices we once visited. So the goal here is not to use every edge, it's to use every vertex exactly once. A Hamilton cycle does all of this and comes back to its starting point. We do not have to include every edge. The goal is just to hit every vertex. So this graph is Eulerian. Let's also show that it contains this Hamilton cycle. So I pick a starting point. And if I go around the graph this way, I have used every vertex and came back to the starting point. I used every vertex exactly one time. And I didn't use every edge, but that's okay. I just hit all the vertices. Explain why this graph doesn't contain a Hamilton cycle. Well, it has to do with these three edges here. That is, I have to start somewhere. I could start in the center, or I could start on one of these triangles. But I have to start on any of the four triangles. And I have to end on any of the four triangles. And it's possible to go through the middle triangle and to across to another one. But it's not possible to hit all three of these triangles on the outside. Because once you go into a triangle along this edge, you can't come back along this edge because you would have to repeat these vertices. And we're not allowed to repeat vertices. Let me show you what I mean. If I start here, I can go around the triangle. I can't come back to here because I'm not allowed to repeat this vertex. But I can keep going. I can go up this triangle. And if I start around up here, I reach a dead end. But if I go down, then I never have a chance to get back to this triangle. I either have to make the decision to go around this triangle or to skip it. But if I skip it, I can't go back. And if I go up to this triangle, then I can't come back down and get to the other triangle. I don't have any way of hitting all three of these external triangles here. And so this graph cannot contain a Hamilton path. A little bit of background. Hamilton paths came about 80 years after Euler circuits came around. It was an alternative to the question that Euler studied. Euler wanted to be able to travel along every street or every bridge in this community for making deliveries and pickups to houses or whatever you wanted to do, but you wanted to be able to travel along every street. If you zoom out, instead of looking at just traveling within a community to traveling, say, touring across a nation, you might want to visit all of the major cities, but you don't really necessarily need to see all the highways. I just want to connect all the different dots on the map. If we find the cities more interesting than the individual roads and houses, this is a different type of question. It's a more natural question. Euler came up quickly with an if and only if condition for his question. We have an Euler tour if and only if every vertex has even degree. But we've been studying the Hamilton problem for over 100 years, and no one has discovered an if and only if proof for having a Hamilton path or cycle. We have a close theorem here. We have a set of one-way theorems like this one here. This is Orr's theorem. It says if we have a simple graph with at least three vertices, and for every pair of non-adjacent vertices, the total degree of those two vertices is at least equal to the number of vertices total, then we're guaranteed that G contains a Hamilton cycle. Problem is, this is not an if and only if theorem. This is only one way. And so we can't go the other way around. There are graphs that contain Hamilton cycles that do not satisfy this criterion. Let's talk about why this works. Let's say we have a graph with at least three vertices. And we want to prove that the graph contains a Hamilton cycle. So we're going to prove this by contrapositive. We're going to assume that the graph does not contain a Hamilton cycle. And then we're going to show then that this inequality goes in the wrong direction. Okay. So we have some graph here that doesn't have a Hamilton cycle. Okay. What we're going to do is we're going to continue to add edges to the graph as long as we do not create a Hamilton cycle. So fill in as many edges as possible without creating a Hamilton cycle. So we could start connecting some of the vertices together. I'm not going to draw all of the connections in. But if an edge would create a Hamilton cycle, we don't fill that edge. So we're going to add edges to G. That would make the degrees even higher, but the degree is still going to be less than n. That's the thing we're going to show. That even if we increase the degree by adding more edges, it still will be less than n. Okay? So there will have to be at least one pair of non-adjacent vertices. If every pair of vertices was adjacent, then I could create a Hamilton cycle just by going through the graph, and then this vertex would be connected back to this vertex here, because every pair of vertices is adjacent. There will be at least one pair of non-adjacent vertices. Call those vertices x and y. Label them x and y. Okay? All right. There is a path from x to y. And here's how we know there's a path from x to y. Under step 1, we filled as many edges as possible without creating a Hamilton cycle, which means x and y are not adjacent, but if I did make them adjacent, I would have a Hamilton cycle. And so without x and y being adjacent, all I have is a Hamilton path. So there is a path from x to y. In fact, it's a Hamilton path from x to y that includes every vertex. So let's label these vertices. I'll call them V1, V2, V3, ... up through Vn. There are n vertices. That's the order of the graph. And so there are n minus 1 edges. Okay? So here's where the tricky step occurs. For each edge, I'm going to look at 2 possible additional edges. The possible edge from V2 to Y, and the possible edge from V3 to X. That is, the earlier vertex to the endpoint, or the later vertex to the starting point. For each edge, vi plus 1, consider vi to y and vi plus 1 to x. I'm going to argue that both of these edges cannot exist in the graph. One of them could, maybe neither of them, but they both cannot exist. Because if they both did exist, we would have a Hamilton cycle, because I could go from x to v2, then over to y, then back to v3, and then back over to x. And that would be a cycle. So both edges cannot be present. So one of these edges has to not exist. So what happened is we went through n-1 possible edges. We considered every possible pair of edges that would connect to x and y, starting from here to here to here to here to here. And out of those n-1 times 2 edges, one out of every pair could not exist. And so only n-1 edges can exist that connect to either x or y. And so the degree of x plus the degree of y is at most n-1, which is less than n. Okay? The next couple of slides type up this idea. If the graph doesn't contain a Hamilton cycle, we're going to add edges to G until we can add no more edges without having a Hamilton cycle. Call this enlarged graph H. Pick two non-adjacent vertices in H. We have to have a pair. Otherwise, if every pair of vertices is adjacent, we have a complete graph, and complete graphs have Hamilton cycles. By the construction, if we added xy to H, we would have a Hamilton cycle. And so without this pair, we have a Hamilton path from x to y. It's just missing the last edge that cycles back to the first vertex. We'll label the vertices along this path. We have n vertices, and so we have n-1 edges. So x, y, and then these are my vertices, v1, v2, v3, dot, 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 up to vn. For each possible edge, we consider the pair x to vi plus 1 and vi to y. That's the pair that we were looking at earlier. Where the I plus 1 vertex goes back to x, and the I vertex goes forwards to y. These edges cannot both be present, otherwise we would have a Hamilton cycle. Start at x, go up to vi, over to y, back to vi plus 1, back around to x. And so since one out of every pair of these edges has to not exist, then x can have some of the vertices, some of the edges, y can have some of the edges, but they can have at most one edge out of each pair, and there are only n-1 pairs. And so the total degree is less than or equal to n-1. All right, see you next time.